So let's do a little audio test. Is that okay? Yeah, that'd be better if it's long enough. Okay, I'll have it in a second here. Sorry. We have another 30 seconds for latecomers. And I'm going to sit down most of the time, but for starters, is this a good place?
I'm focusing on the screen.
Okay, great. I can sit down now. Okay, well, good morning, everybody out there in Internet land. My name, as it says, is Glenn Orstone. There's my email address, which you can feel free to email me with questions or whatever. And I'm going to talk about a version of Forth called MeCrisp. And along with my talk goes a free CD with a whole bunch of stuff on it, documentation that I made. And the only issue with that is that there's a really bad error in the ones I made that I discovered at the last minute, too late to change. And so I'm going to do an update for that. And while you can take one today, I'd prefer that you just give me your email address and I'll mail you a better one. And of course, thanks to Matthias, the author of MeCrisp. He lives in Germany. This is a part-time fun thing for him to do, which means this is so good that in my view, he's an outstanding programmer because, like I say, this is just a hobby. His real work is a PhD in biology that he's working on. Okay, what is it? Well, it's mostly ANSI Forth, which means for you experienced people, it's really easy to use. It's subroutine threaded, and a short comment about that is most people seem to think that that's not really the quote best way. It seems to be that the direct threaded code is what seems to be more commonly thought to be best. But one of the advantages of doing it this way is that he has included in there a lot of optimization, which I'll talk about a little bit later. This runs out of the box with almost no effort on a great many different boards, more than a dozen. And they're all in one of these two families, the ARM Cortex, various of the low-end ones, which is practically the world standard these days, and on some versions of the TI MSP 430. And this the TI ones come in both MSP 430 and ARM versions. There are several different of the ARM versions and several different of the MSP 430. And there's a thing called Launchpad from TI that's really inexpensive that you can use. And this might be a good time to show you a picture of what some of those boards look like. One that I think is the best bang for the buck is an STM called Nucleo board. And this comes in several different versions that are supported by MeCrisp. Is that a good place right there? And these things only cost about $10. And like I say, there's something like that.
There you go. Perfect.
And so these are about $10 each for each of several different varieties. And the one that is really good, somebody's telling me to do something. Anyway, and the one I think is the best bang for the buck, perhaps, is called a F401 that has 500K of flash memory, which is a lot, and 100K or so of RAM. And so that runs Forth very nicely. You need at least 32K of flash for this thing for MeCrisp to run well, although it will run with only 16K on some of these boards. So let me show you some more. The one I'm going to use in the demo today is a TI Launchpad MSP 430 with FRAM, and I'll talk about that a little bit later. And this one has 128K of flash and a couple of K of RAM. So that's, of course, a lot of memory to run MeCrisp. It's plenty. This board costs about $18 or so. And if you're serious about really trying this, this is the board that I'm going to use in the talk today, by the way. when I get around to showing a couple of demos. So if you're serious about trying this out and you're okay to spend a little bit of money, that's a good one. And then there's some other ones that I won't talk very much about. Like I say, there's more than a dozen different boards. This is another one from TI, and this is an ARM Cortex M4 board that, if you like TI, is a pretty nice one. Supported is a dual inline package chip from NXP. I think it's called an LPC 1114 or something like that. And if you want to breadboard your own, this one's built on strip board. Doesn't look very good, but it works. And so you can, this is one of the cheapest ways to do this, to try out MeCrisp, because you make your own little board using this part here. These parts have gotten more and more expensive in time as NXP has realized that it costs them a lot to make a dual inline package like this compared to surface mount. The cheapest probably is this board that comes from China. When you download MeCrisp and read the README, you can find out all about these different boards. And the main disadvantage of this one is that these pins here that you use to connect to whatever you want to connect to for I/O are not on 10th-inch centers. That's another problem with the so-called Arduino boards. They also have that problem. And so I typically don't use those for that very reason. Okay. A friend and I have launched a project to make a PC board. And that is the preliminary version, the beta, you might say, of that, just came yesterday, and one has been loaded, and I was supposed to have it today, but there were foul-ups along the line, so I don't have it. But here's a breadboard using that part, and you, whoops, forgot that that wasn't attached. The other side looks like this on the breadboard, so it's made on a single-sided, sorry?
Coppery.
Yeah, single-sided blank PC board. And this side looks like this. So you should be able to see in there the part itself and all the wiring to put it together. And this connector up here is used for programming or for I/O. And there's not much on there except a light. So this runs a blinky program. It doesn't do much more. It's kind of a breadboard of this PC board, which is now available. And oh, I wanted to say one more thing briefly about this Launchpad board. It has a nice LCD display, which is really handy. This little LCD display here, which costs about $5 in small quantities, is supported by our new PC board and also by that NXP dual inline 28-pin part that I showed. This has actually been tested on that one. It works great. If you need an 8x2 character display, that's a nice way to do it. Okay, let's see. There's one more thing to say about programming these things, but I'll get to that. Okay, so here's how you get started on this thing. Google on MeCrisp and you'll find a place to download 2 different versions of this thing. Let me see if my pointer works here. Yeah. If you want to do the MSP430, the latest version is this one right here. And you download that and extract it or decompress it or whatever, and you'll have a whole bunch of stuff to look at. By the way, this presentation is for Linux. I don't use Windows, but this will work on Windows. That is, this meaning MeCrisp will work on Windows. We'll have to do some effort, mostly getting a terminal emulator running. And if you want to do one of the ARM Cortex versions, then you download this thing here and extract it. And for either one of these, the next thing to do is there's a nice README in there that tells a whole lot about it, and you'll want to read the README. Gee, it says that right there. Now, each different distribution, like I say, there's more than 12 of them, has some examples. And you should really look at all of them because each different distribution has an example or so that will probably work as it is on some of the other distributions, at least if it's in the same family, the Cortex or the MSP430 family. And so you can learn a lot about looking at the examples. And there's also a common file that has sort of common examples. You can try this for free in a couple of different ways. For the ARM version, there's a little development board from Freescale that's called this right here, I believe. And there is a software simulator that's meant for that version, but it works with any of them really, except of course, when you're simulating, you don't really get to do I/O, but you can play with saying and try it out, look at registers and see what it does. For the MSP430, one way to simulate this for free is download this program called Naked ASM assembler, and it has a utility program that has a simulator in it. And while I've not tried this, I'm pretty sure that it will work just fine. So that's a couple of different ways of trying this thing for free if you want to. I recommend, though, if you're at all serious, buy one of the development boards. They're so cheap. The cheapest one's about $7. The one I recommend is about $10, or one of the TI launchpads if you want to run the MSP430. They run from $12 to $18, and the one I'm showing today is the most powerful of those. That goes for about $18. One of these, by the way, one of these boards will connect to the internet. One of the launchpads has support for an internet connection if you need that. There is an experimental version, which is pretty interesting. And you'll find that when you Google on the MICRISP site. And this one does a couple of things. I believe that it'll run on an Android laptop, I think. You'll have to read the README to get squared away because I haven't really tried that. So that's a way to try it on your PC directly. And this has another little neat thing. As you already know, I'm sure, since you guys are all the experienced fourth people, if you keep the top of the stack, the parameter stack, in a register, there's a significant speed up typically, making code faster if not smaller. And this experimental version keeps more than one, essentially, parameter stack in registers. And because of this optimizer, sometimes code will execute without really accessing the software stack at all, only accessing registers. So that's kind of neat if you want to experiment with that sort of thing. I must have pushed the wrong button here. Let's try that again. I already talked about some development boards from $7 to $20. I talked already about, sorry, this mouse is, talked about the one that has lots of flash and RAM that's really cheap. This is the $7 board from China, which is difficult to install. And if you want to try that one, did I show that one? I don't think yeah, I did show that one. That's the smallest and cheapest of the ones. It does not have pins on into centers, but still it works. By the way, I've tried all of these. I've tried most of the 15 or so that are supported, and they all seem to work just fine. I haven't discovered any bugs yet. Anyway, that one, that particular Chinese board, the $7 one, is somewhat difficult to get installed. The README is not really, it doesn't really talk about how to do that. So you can send me an email if you want to try that one. Personally, I wouldn't bother with it. I'd try one of the other ones. And the one with the dual inline 28-pin package that I talked about is all very straightforward and works just fine. And by the way you get MICRISP loaded into all these is pretty clearly documented on the website, with the exception of this one. And the MSP430 ones it's not entirely clear for those, so I'm going to talk about how to do that here in just a minute. This is the one I like best. One main difference between MSP430 boards and the ARM boards is This is a 16-bit processor, and the ARM ones are all 32-bit processors. And of course, the ARM ones are built by a number of different companies. So you're not really single sourced if you're going to use an ARM, where you are if you use the TI part. Some of these will need an FTDI USB to serial dongle to run, and some of them won't. The STM boards do not need that. The TI Launchpad boards don't need that either, but some of the other ones do. And how to do this is fairly well documented in the README. And then finally, as I maybe mentioned, a friend and I are working on a development board. We got the first betas a couple of days ago. One of these has been loaded and tested, and it works just fine. I meant to bring that today, but my partner forgot to give it to me. And it has 64K of FRAM. I'll talk about FRAM in a minute. 2 serial ports, which is really nice if you're running Forth, because one serial port is dedicated pretty much to running micrisp Forth. And if you want to use a serial port for something else, in addition to that, it's nice to have a second one. Like I say, you really need 32K for this to run nicely. 64K is even better because you can put all kinds of stuff in there. And we're going to get 50 of these boards here pretty soon. If you want one, we could probably work something out. So let me talk about some subroutines that you can load once you get the basic micrisp Forth running. There's a prompt that I put together, and that's on the distribution. You can find it in there somewhere. I don't remember where exactly. It's also on the CD. And what this does, okay, this is a matter of opinion. My opinion, it may be different from everybody else's in the room because you're all used to running Forth, and I'm basically not. But I think prompt should start on the beginning of the line like it does on every other tool in the universe that I know of. And words has a meaning that is true everywhere in the universe except for Forth people when it means something entirely different. So I try to remember to put that in quotes when I'm talking about Forth style words, and not in quotes when I'm talking about every other kind of word in the universe. And so, for instance, the MSP 430 is a 16-bit word, and the ARM Cortexes use a 32-bit word. Oh yeah, here's another nice thing about prompt. I think like most Forths, there's a couple of modes, and I don't particularly like modes, but that's the way it is, and I can live with it. So one of those modes is whether you're compiling to flash or to RAM, which is extremely useful because you're trying something out. It's nicer to just compile it to RAM. It's easy to get rid of it that way by pressing reset. And then when you finally get the thing working the way you want, you can do a compile to flash. So that's one of the modes. And it's nice to know what mode you're in, because if you don't remember, then you're going to, when you load something, you might put it in flash when you meant to put it in RAM, or vice versa. So that's nice. And this prompt tells you what mode you're in. And then there's also, are you in hex, decimal, binary, what kind of mode you're in that sense. And it's nice to know what that is in case you forget. You guys are also experienced. You don't need this perhaps because you never forget, but I do. So this is a thing that works nicely. Now, Forth, in my view, is really great for embedded systems, which means I/O intensive, often not compute intensive. So you need access to I/O without too much trouble. And some of these parts have many, many different I/O registers with different functions. You can define constants for all of those. In some cases, you'd be defining 1,000 constants. So I thought of a way to make that a little simpler, and I created this thing called I/O definitions. And by the way, when it's a Forth program, I use a .fth extension, but micrisp, as you download it, uses a .txt extension for both text files and for loadable files. So I just changed that to make that a little more understandable. And we'll talk, I think I have a slide on this later. And then long comments, well, that's really nice. You can have multi-line comments if you want, and that's handy sometimes for documentation. And there's a little thing called blinky. That's just the sort of minimum thing that you can get it to do something that you can see, blinks the light. And John Baumgartner, which some of you know, and some others have made some other contributions, which you can find on the when you download the MeCrisp files. So in MeCrisp, this backslash is a end-of-line comment character. And so here's what prompt looks like. It shows whether you're compiling to flash or to RAM. It shows the mode, dollars meaning hex, and this meaning decimal, and I think it's a percent sign, it means binary. And this is the number of words on the stack. So I find this to be really helpful. If you don't need it, don't load it. So here's then, once you get a prompt, this is the little prompt character right here. This is, as I mentioned at the beginning of the line. And if you do a 1, 2 plus, everybody knows what that does. And this shows that now there's one word on the stack. Of course, if you want to know what it is, you just type dot or print character and it'll show you, hopefully 3 in this case. Oops. So I mentioned optimization. Here's an example. I'm going to define a quote word called food that adds 2 constants together and prints the result. By the way, if you have any questions, interrupt me. But I think for experienced fourth people, all this is already enough to put you to sleep almost, except this really is important about the optimization. So there's this word called C that's really nice that I think is common. And so what we see here, if we do C, is some of these, in particular, the Cortex M0s have only one hardware support for one stack. So you have to, oh, and by the way, well, I'm not going to get into that. There's support for one hardware stack. MeCrisp uses a software stack as the parameter stack. So the first thing you have to do is you kind of decrement the stack pointer so you have a place to put something. And then in this case, then remove, and here's the key. We don't push a 1 and a 2 and then add the 2 together. The optimizer says, well, those are constants and added together, they're 3. So we just push the 3 under the stack. It doesn't add the 1 plus 2, doesn't need to. And then this is a call to the print routine. So that's, this optimization turns out to be really, really handy in making the code smaller and faster. Is there a question?
No, sure. Comments, does C print out those comments? Or did you add the comments in?
This, okay. Yeah. C prints, actually that's a good question. Honestly, I do not remember whether
I would really like to know how you get those comments if it prints them.
Well, that's a good question. Like I say, I honestly don't know. Either I put them in.
I strongly suspect that it was edited after C in its work.
Yes.
I suspect that too.
Yes.
Let's go with that theory.
Let's move on.
But the comments, but you can of course look at
decompiler, disassembler that will add comments.
Yeah. So I think Kevin is probably right, but the straight answer is I don't remember.
Okay.
But of course the comments will be in the source because I would have put them in the source.
Yes.
But yeah, that's a good question. But the rest of this stuff C does, like this little dot here. It says we're calling the quote word called dot or print. And it shows that definitely. The only thing that I probably added here is just the comments, nothing else. It shows where they are in memory. In other words, this print routine is right here in the memory. And then, oops, and then the subroutine return, it doesn't say subroutine return here. This, you have to understand the TI MSP 430 assembly language to realize that this is a return from a called subroutine. Okay. Any more questions about that? C is really, really nice. And that's one of those things that you aren't going to get with a 16K flash or FRAM because it's just not big enough. So that's why I recommend, if you're really going to mess with this, I would just forget all about the 16K versions of various things, which is really only a couple of them anyway. Most of them have more than that. A word about words. Well, I already told you about the definition of words. But in addition to, well, I'm sorry, not in addition to, but there is a fourth word that shows where things are. And I didn't show the whole output of this because it's pretty long, but it shows where things are in memory. I hope the pointer shows up reasonably well here. It shows flags, and flags have to do with optimization, which I'm not going to talk very much about. You can learn all about it by reading all the source code and the documentation that comes with Nyquist. The link is, you know, a dictionary is sort of a linked list of things, and this shows where the link to the next thing is. In this case, we see a D418 is the next thing, and there it is right there. And then the name of the thing. And so this, if you do a word, you get two things really. You get the listing of what's in the Nyquist core, and then it's not shown here, but you'll get another listing of the things that you've added to either flash or RAM. So that's a nice thing to have. You can, one thing that would be nice to know is how much flash or RAM do you have left? Are you in danger of running out? Well, it's easy to figure that out by looking at words and doing some calculation if you know how much flash your device has in the first place. But one of you experts could write a word, a fourth word that is, that will show how much you have left. I think that would be a really nice addition. Matthias would give you credit and add it to his website most likely if you did that. Of course, I can do it too, and one of these days I will if somebody else doesn't do it first and email me the result. So I talked about I/O definitions. This is really important if you're going to do I/O. Instead of having 100 to 1,000 different constants, you can have approximately 11, I missed one, for this particular micro. How many there are depends on which micro you're using, of course. How much I/O does it have? But the one that I'm using today has 11, and I didn't put the 11th one in there. And then you have definitions for all the different things that you can do with I/O registers. Input is, you know, what's coming in on that register, or the output is what's going out on that. And the direction is defining, is this port an input or an output, and so on, for all the different things you can do here. And so this makes about 20 something instead of 100 or 1,000. It's a little slower and a little bigger because these aren't constants, these are subroutines. Any question about that? I think that's straightforward.
Well, this just describes what a port, what all the different, how you can configure a port.
These constants are one for each port that the device supports, but then each port has a bunch of different registers that let you do output or input, or select what kind of a port it is. That's these SEL things. That a port might be different things. It's not just necessarily a GPIO, like you might have a serial port or a I2C or whatever. And these, you have to read the documentations for the device to figure out how to set these, of course. That answers the question, I hope. So here's an example. This one requires this I/O definitions file, so it shows you how it works. So we're going to say, oh, bit numbers are defined already in, I think they're in the I/O defs file, as I recall. And so this is the port we're going to use. This defines the direction. So the direction of bit 0 of that particular port is going to be an output. If you set bit 0 to 1, that makes that pin of that port an output. And I did the same thing for a P9 port. And now down here there's a begin until loop that says this is going to run until you press a key. That key up returns a 1 or a 0 depending on whether a key has been pressed. And so here we're going to do this bit 0 on P1. We're going to send that bit to the output port of port 1. And this is a XOR function. Store, of course, you need that. So this does changing the state of that bit on that port from 0 to 1 or 1 to 0, whatever it was before. And this does the same thing on a different bit on a different port. And then there's a loop that runs until you press until. So this is a nice, and this particular one is for this thing here, but it would work on anything if you just get the ports set to where you have a light emitting diode. So it's not specific to this particular launch pad. And this is a really nice thing. Once you get this thing up and running, this is nice for a test to just make sure everything works okay. And it'll be, this is a software loop, so how fast it blinks depends on how fast the CPU is running. There'll be a default when you start it, which for this particular board in micrisp is 8 megahertz clock. So let's look at some more things beyond getting this thing running. You can load this file that comes with micrisp forth that gives the C and another thing called list. List is like words, except it's a lot shorter and it doesn't give you all the detail. So that's really handy, it turns out. And you can load the assembler. This is a really nice thing about the MSP 430 version. There's a really nice assembler there, which means you can write assembly code, and I'll have an example of that here in just a minute. So that means, to me, it means you can develop your code using high-level forth and then figure out where it needs to be sped up because it's too slow if it is in some particular area. You can recode that particular part of the thing into similarities, and it'll go a lot faster. Maybe not a whole lot, but noticeably faster. So what this means is you can make forth words or subroutines go just as fast as if you wrote them directly in assembly language. There's a multitasking example in the distribution. If you want to do a multitasking, I forget whether it's cooperative or preemptive. I don't remember, but anyway.
That was my question.
Yes.
Is it cooperative or preemptive?
That's just what I said. I don't.
Yes, I know.
Is it in high level fourth or is it in?
It's in high level fourth. And I'm sorry, what was your question? What's the difference between?
No,
That's what I wanted to know.
Oh, yeah.
That's my question.
Read the documentation.
Read the document.
I think that it's preemptive, but I don't know for sure. I will tell you that to the best of my recollection, it has separate stacks, which is a requirement for a preemptive fourth and not necessarily for a cooperative. Although in general, most cooperative multitasking does also have separate stacks for each task, but it isn't necessary if you do some tricks. And if you want to know more about that, I wrote a cooperative single stack multitasking thing. You can probably find it on the web too if you look that up. Anyway, it definitely has separate stacks for each task. And I already mentioned that you really should look at the examples in all the different distributions, because like this multitasking, for instance, is not really in all the examples, but it would run on most of them. And we'll talk about benchmarks. There's a wonderful book called How to Lie with Statistics. Anybody ever run across that? It's kind of an old book, but we don't have any teenagers in here, so you might have run across that. Well, I could say how to lie with benchmarks, because the only benchmark that's really any good is to code your complete application, debug it, getting running on it on your different languages that you want to try, and then measure the result. That's the only really way to do a benchmark, but that's too much work, so people take shortcuts, especially if they want to try to prove something. Okay, so here is a minimal, I would say, Blinky that I was using to test the speed of things. And this one doesn't return. So once you start this thing running, it'll go until you hit reset or turn the power off. So what it does is, in this case, I wasn't using IODEFs. I had coded constants someplace for P1 DIR and P1 out. And I didn't show those here, but those are just a couple of constants, and the bits are constants also. So what this one does is a continuous loop, again. It toggles the red LED, which is bit 0 of port 1. So if you want to run this, you have to change this to whatever you have for your LED. And then it does a loop. As I said, the word length in MSP430 is 32 bits. So this thing here loops as many times as it can using a 32-bit word. You can also, by the way, say 00 do. I didn't do that because it might be confusing, but that does the same thing, I think. So I mentioned you can use the assembler, and here we have shown the constants. This thing isn't showing the spaces here very well, I see, but they're there. Otherwise it won't work. So we have defined constants for the ports, and this is a kind of a neat feature of the particular built-in assembler. Instead of directly using labels, you can use this symbolism right here of a L minus, and this J and Z means jump back here to the first minus you find, and then this one I think back to the second minus, or is it, yeah. And so I don't want to go on and on about that. This is just a nice way to do labels. You could put ordinary labels in here and it would do the same. So in this one, what we're saying here is we're going to set bit 7 is what this amounts to. Set bit 7 on the port 2 direction, which is where the LED is. So we're setting that particular pin to an output. And then here's the loop, the endlessly running loop is we're going to do an XOR of that bit, which means change the state of the LED to off if it was on and vice versa. And then we're going to decrement R4. And since this is a 16-bit word, and when we decrement it, if it's not 0, we go back up here and toggle it again. I'm sorry. Can't remember how my own code works. I think this might be a bug, actually.
Yeah.
I think we have a bug here. What we want this to do, if it's not 0, we want to go back right up here to the decrement line. So this is the one that should have that L minus on it right here. And then if it is 0, we want to go back up to this line right here. So we just found a bug, but I'll go over it again just to make sure it's clear. We're going to decrement R4 until it's 0. And then we're going to go up here and toggle the output pin. Now, if R4 is 0, then when we decrement it the next time through this loop here, it won't be 0 anymore. So it's going to remain in this short loop here, decrementing over and over again, 536 times until it's 0 again, and then it'll toggle. Okay, hopefully that's clear. Sorry for the bug. Unlike some of you, I sometimes make bugs in my coding. This might explain another bug. This isn't doing what it's supposed to do. When I did the benchmarks, there was a problem. Here's the C version. Okay, so this MSP430 series is very easy to program in assembly language, C, or Micro's Forth. By the way, there are some other Forths that run on this too. I think Dr. Ting wrote one, as I recall, which is a nice one too. And heck, try them all. See which one you like. Anyway, not to belabor that point. Here's the C version. I'm not going to talk too much about this, except this. Can I highlight this? Whoops, no. There's a little piece of magic right here with the FRAM versions of the MSP430. If you start using this, you'll run into this right away. This is an extremely low power device if you set up your code to make it be so. And that's one of the big pluses of the MSP430s. And the FR versions work a little differently than the other versions in that to get the power even lower, when you boot this thing, all the I/O is turned off to save power. And you need to turn it back on again. I'm not going to go on and on about that. It's just a little thing for you to remember if you start actually trying to use this thing. So this in C means the exclusive OR, same deal as everything else. We're changing the direction, and then we have a loop. This in C, this is an endless loop where we're going to toggle the LED pin and then go through this little loop 65,536 times, and then go back up here and toggle the pin again, and so on. And that runs forever, just like the other ones. To end it, you have to press reset. So we have benchmarks here for assembly language C and forth. And so I ran all these and timed them. And here's where I have to make a little note. The CD, if you want one, has a big bad error in the results of these benchmarks. And I didn't have time to fix that. So if you want one of these, please remember that those benchmark values are bogus and you should ignore them and run your own and fix whatever I did wrong. I prefer that you not even get one of these CDs. Give me your email address instead. But if you really want one today, you can have one.
One of the things that you have to be aware of when it comes to C is function main. Main gets called after initialization. Okay, there's this, and usually if you look at like any PC code, you see it, the execution starts at a label called start, and it goes through all this gyration. And that's probably the reason why you have to do that PM5 CTL0 and clear the block LPM.
Yes.
Because it probably gets set in before main gets called.
That's a very good point, and thank you very much for pointing that out.
Yes.
If you're coding in C, my view of the bottom line is if you really want to know what's happening, you need to look at the code for the initialization that is done automatically.
Exactly.
And if you don't like it, you can change it.
Yes.
That's a tricky thing about C. That's one of the things I like about Forth. It's just like a assembly language. You're the master of all this. You do what you want, and you know what it's going to do because you wrote the code to do it.
Usually see it for when you're running on an operating system.
Okay.
You can go and do it, embedded, straight, but you got to know what start does.
Absolutely.
And it's usually called in C. It's a library function called CRT0.
Yes, I believe that's right.
Language.
And on the next CD, I'm going to have a lot more about how to run in C. I didn't even bother to put it on this one because this is a Forth group. However, I think why not go ahead and put that on there? Because I have a lot more information about that from the C expert, who's the other half of our partnership doing the board. And I'll add some of that later. But to reiterate, there is some initialization code, and you need to figure out what it actually does so you can make sure that it does what you want. And one of the things it does not do is this little thing here you have to do to get the I/O working. Now, it turns out that when this thing boots, or when you turn the power on, there are defaults for most of the registers. And the default here is that this thing is turned off. That is, that the I/O is disabled. And I believe that the particular default C header for this does not enable that. So that's why you have to do it here. In assembly language or whatever else, Forth, whatever, you have to do it too. Now in MeCrisp Forth, that is done in the initialization. And so that's why you didn't see that in the examples I showed for MeCrisp. As I say, there's a lot of, see, the reason I started really focusing on Forth was because all my past programming has been in assembly language. Well, as these devices get more and more complicated, that gets more and more tedious and error prone. So I decided to start using Forth. And I found that that's much easier than using C. Now, I will say that for embedded systems programming, which is what we're talking about here, C is pretty much the standard. That's what almost everybody does. but you have to know a lot more about make files and linker files sometimes, and all kinds of, and these header files and that kind of thing to use C. So it's really more trouble, I think, and not as close to the machine. You can't do everything you want to do in C. And so that's why I like Forth. But since I have an expert in C on this project, I'm going to try out some C code also, especially since, okay, I'll digress slightly to talk about this breadboard a little bit that we built, or this PC board. We spent a lot of time deciding what part do we want to use. The ARM Cortex parts have big advantages, but I won't bore you with the details. I decided that I like the TI FRAM parts better, and that's what we selected. And we have selected the 38-pin version that's in a package called a TSSOP, which I've found through practice is not very hard to solder. So it's kind of breadboard friendly in a sense. And it has a lot of features that I wanted. I won't go into all the details, but the bottom line is that's the series that we selected. And of that series, there are two in particular that I like. One of them is the one that's on this breadboard that I brought. It's a 64K of FRAM, and which means it runs Forth very nicely. And Forth is supported on that particular part out of the box, and so I didn't have to modify anything. But that one costs about $5 in small quantities. And the cheap part has 16K of flash. It will run Forth, but really not very well because it's not enough. But it will run C or a similar language just fine. And that part in small quantities is about $1.38. So that's a really cheap part. So those are the main two that we're focusing on, although we'll run some other ones. And what can I say? Well, because that part is so cheap, that's why I'm interested in trying out C. I've already done lots of assembly language, so that's not much of an issue, but I'm interested in trying out C on that particular part because it's just too small to run Forth. Okay. Any more questions here? In Maker's Forth, you can redefine interrupt vectors, which probably everybody knows. If there's an interrupt generated by some signal on some pin, that will cause some code that you have defined to go run preemptively as long as your interrupt system is turned on. And you can redefine those interrupt vectors from their defaults to where you have some code that you want to run when there's an interrupt. That's a very nice feature. Already talked about multitasking. It says here that it's cooperative, but you better verify that because I'm really not sure. And it says there are 32 stack elements for each task, which is probably enough. And if you want to know more about this, read the documentation. Some of the documentation is not quite as clear as it could be, but if you do a little work and make use of that fourth word called C, you can figure it out pretty well, I think. So supposing you want to run this thing, you can download for free a TI software package called Energia, or however you pronounce that, and extract it. Now, there are many different versions of MSP debug out there, and if you just Google on this, you'll most likely get the wrong version. The way to get the version that works is you find that in this package here someplace and put it in your executable path. And if you run Linux, you can figure that out. If you run Windows, you're on your own, but you can do it. And then there's another thing in there that's a library that you're going to need called TI Lib. You find that, it's in there somewhere, and move it to your library path, which in my case is / well, I forget what it is. But again, you're a Linux expert, you can figure it out. Or you're a Windows expert, and you can, with a little bit more work, figure out how to do it. And now, how do you program these things? There's two easy ways to do that. We're going to use MSP debug. Oh, and by the way, just as a slight aside here, if you're using one of the ARM Cortex versions, it's pretty well documented how to do that for each different distribution of the ARM processors. It's really very straightforward on all of them except the Chinese one. And so I don't really need to even talk about that here. But this one's a little more tricky and not clearly documented how to do it. So let's see. The two different ways of programming this thing that I found particularly useful is there's this little dongle from TI called MSP-FET. This is what's most easily supported on our little PC board. And but this gadget is $100. So if you're real serious, it's worth it. But if you just want to play around, there's a cheaper way to do it. And that is you get, yeah, JTAG. Well, it's, you might say a subset of JTAG called SWD serial wire debug. Actually, it turns out this one will do JTAG too. So if you have a port that supports either JTAG or single wire debug, which is like JTAG, only slower and uses fewer pins. So for the devices with a small number of pins, the serial wire debug is really nice. And some of the MSP 430s only support that. Some of them only support the other. Some support both. The parts that we use all support either one. So it's just, you want speed or do you want more pins or whatever. The other way to program these things is buy one of the launch pads. The cheapest one that will work is about $12. Don't buy the MSP 430G version because it doesn't work very well. But any of these others do. And you'll just jumper from 4 pins on this board to 4 pins on the board that you're using. VCC, the plus 3.3 volts, ground, the reset and the test from the launch pad to the whatever device you're using. And this works just fine. Especially if you don't want to spend $100, you'll have to spend about $12 to do this plus 4 jumpers. And then once you get all that done, you have already installed, I didn't show this on here, but you've installed the MSP debug and the TI lib, as I talked about in an earlier slide. And so in Linux, you do this, you might not need this, which means run as root. But you do that, and then you're off and running, and you have a little debugger that lets you program, look at registers, do all kinds of stuff. Really easy to use, reasonably well documented. And that's how you do it. To get a program in there that I'm talking about, if you actually want to run it, you need, of course, you need the 4th version that you've downloaded and installed. And to run 4th, then you're going to need 2 little programs that's in your distribution, almost certainly, called Minicom and Picocom. These are terminal emulators. The only reason you need this one is it has a subroutine that this one needs. There's probably better ways to do it, but this works and it's easy. If you want to do something in assembler, you download this assembler, but again, it's free, works just fine, and put it somewhere where you can find it. And if you want to do it in C, you download this free thing that you can find on the web and read the docs or get that installed and running.
There are a couple of other companies that will sell you a single wire debug JTAG pod. This one here I'm looking at is from Tag Connect, and it's $64. So,
Okay, good. I don't know if
and there are cheaper ones.
I don't know if the internet audience heard that, so I'll repeat it. These methods that I've mentioned for programming and debugging this thing are certainly not the only ones. Companies sell single wire debug boards that are less expensive than the TI one that will do this job also. So if you do a little Googling, you can find out how to do that. It is my view that the absolute cheapest way is to use one of these launch pads. However, it has one disadvantage, and that is your board is going to be running at whatever voltage this thing puts out, which is 3.3 or 3.6, somewhere in there. I don't remember exactly. If you want to run with a different voltage, for instance, you want to run with a battery, then you'll have to program it using the voltage that comes from the launch pad. And then, of course, when you run it, it'll run on the battery if you set it up that way, but it won't be running with the same voltage that you programmed it with. For the most part, that doesn't make any difference, but it might under certain circumstances, like the DCO frequencies might be a little bit different if they're running on a different voltage and that kind of thing. So I don't think that's a very big disadvantage. but it is just something that I wanted to note. That isn't true with the MSP FET. You can run that thing at any voltage you want. So if you want to try out the C compiler, well, here's the way to do that. The other two ways of doing this are easier, but like I say, this is kind of a default in the embedded systems programming world, and you might want to do it that way. The main, or perhaps the only real disadvantage of using micrisp is you really do need more flash or RAM memory, where these other two methods will work on parts, depending on, of course, what code you're trying to run. As small as the smallest part might have 1,000 bytes. And you can write useful programs in 1,000 bytes if you use assembly language, or even if you use C. About speed and size. Okay, this is big because you've got 11K bytes or 12K bytes of fourth resident in your flash all the time, plus whatever code you've loaded in there. So this is going to take the most code. This, if it's carefully written, will take the least amount of code, assembly language, if it's carefully written. But what about, and this one is somewhere in between. What about debugging time? Well, in my view, the fastest way to debug is to use fourth. The slowest way is probably assembly language, and C would be in between. So you got to count that too. If you're building 10 million of these, you don't care how much the software tools cost. You won't be using these free tools. You'll be using probably an IAR, multi-$1,000 compiler. You'll be writing it in C. You'll have lots of support, blah, blah, blah. You're running 10 million of these. It doesn't make any significant difference how long it takes you to debug and get the code working nicely. But none of us are doing that, most likely. So in terms of speed, assembly language, carefully written, of course, is going to be the fastest. Slight digression here. I have till what time? 11:30? Ish. So we're fine. Yeah, I think it's going to work fine. I have time for a slight digression. In the old days, I was put off by a couple of things about fourth, and one of them was the claim that if you write it in fourth, it's going to be faster and smaller than if you write it in assembly language, or C for that matter, which is of course completely ridiculous. Nobody says that anymore, I'm happy to say, but I just had to mention it as something interesting.
We should have a lot more high-level support with fourth than do with assembly language. And I don't see a lot of kids nowadays learning assembly language.
Okay, the comment was not many people are using assembly language or learning assembly language anymore. I think that's true as far as I know, except maybe in some certain computer science classes. You might learn it just so you know about such a thing. Might, yes, or might not. As I've said before, the default in the world is to program in C for embedded systems programming. I think the comment was that, was it that the debug might go faster in fourth? Is that what you said?
What I meant was, yeah, it goes faster if you do it in highly optimized assembly language. But when you use fourth, you get a little more high-level programming support there.
Yes.
More concepts, you know.
Okay, the comment was that you get more support, really, high-level support, if you use fourth than if you use assembly language. In assembly language, you're pretty much on your own, except maybe you can find some examples that will help. But fourth is definitely a higher level language than assembly language, quite a bit higher level in my view. So my own opinion is debug will be faster if you do it in fourth. And you don't need some kind of separate debug program either. I like Maker's fourth, if you haven't got that idea yet. And I have a whole bunch of projects on my list to do. I doubt that I'm going to do any but the very simplest ones in assembly language, and I might not even do those in assembly language. I'll be using either micrisp or C. And for those parts that are big enough to run either, I haven't really decided which I'm going to use yet. Anyway, let me see. I think 3 different ways of running stuff in these 3 different languages. Okay, before I do a conclusion, I'm going to do a conclusion and then I have some more comments. I believe that this is really a very, very good implementation of Forth. And so if you want to experiment with embedded systems programming, I highly recommend that you at least take a look at this. I think I mentioned you can do this for free running some simulators, but you won't get to do any I/O. You can sort of, you can sort of get an idea if the I/O is working or not by writing a little code, and you run this thing, and at the end you put something in the soup, so it's just sitting there. Then you stop it and use the MSP debug to see what's in registers that you set up. So you can get an idea of whether the I/O stuff is going to work or not, especially for simple things like GPIO. If you're trying to do a serial port, you're going to have to actually run it on real hardware to make sure it works. Why did I say 1K? I certainly didn't mean that. 16K is the right number here. Another bug in the slides. It's going to need about 16K for a minimum install of Forth, which means it won't run on the really small ones. I'll come back to that. Hardware is so cheap these days, well, don't scrimp on it. Especially if you're only building 10 or something of these things. It's a complete waste of your time to skimp on the hardware. So in the case of MeCrisp, go ahead and spend $5 for the 64K part. That's a really nice part with a whole bunch of really nice features. It's got CRC built in. It's got a real-time clock, which is really nice. It supports a watch crystal or a high-frequency crystal if you want. But if you're using the real-time clock, you need to use the watch crystal. It's got some other really neat stuff, some of which I don't even remember. I think there's a support for a pseudo-random number generator in there, but I can't remember. And some other stuff. This is a really nice, and I might say complex because it has so much stuff in it, a really nice part. That's the 64K version of the TI MSP 430 FR, which stands for FRAM. Oh, I'm going to talk about that in a minute. CD has lots of info. If you wait for the reorganized or redone CD, it'll have some more. Not only are there some bugs on the current one, but there's some stuff that's missing. Feel free to email me with questions anytime. If you want one of these little development boards that we're making, it's going to cost you more money by a little bit to put that together than if you just buy one of the launch pads.
Do you have an idea of what the price target's going to be?
Well, we're paying for the board itself a hair under $6. Then you got to add a part, and you got to add a few. That is a macro.
Are you going to sell an assembled one?
I doubt it, but it is possible. Our plan is to get the thing working nicely first, and then think about if we want to sell boards. I don't want to get into, I don't want to be a company. Okay, I'm retired. I'm having a lot of fun. If you run a company, there's a lot you have to do that's not fun. So I don't know yet. But for this group, I'm going to ignore all that, probably do something illegal, which means not charging sales tax, because then I have to remit it and all that. Don't tell anybody I said that. And it'll be just for this group, just very small quantities, a couple of boards to try out. The nicest thing for everybody is just go buy a launch pad instead. Or if you want to do ARM, you know, you buy one of the many ARMs that are supported. It's cheaper. If you buy this ARM Nucleo board, the instruction set is better, I would say, and certainly more powerful than the MSP 430 instruction set. It's got lots and lots of flash and RAM and all that kind of stuff. Just buy one of those. If you want to do an ARM, buy that STM Nucleo board that I mentioned, the F401, or one of the others that's supported.
So what are the advantages of your board? You might want to repeat the question for the internet.
That's a good question. Thank you. I forgot to do that. What are the advantages if you want to try to use one of these boards that I made, or the breadboard? It's really easy to make these breadboards the way I did it, and I'll document that on the next CD. It's not on this one. So what's the advantage of our little board? The main advantage is it's something that I wanted to do. I'm retired. I do all this for fun. I thought that would be fun. It has been really fun. And my partner in this effort needs a bunch of little boards to do various different things. So he needed a little board. The store-bought ones that are so cheap aren't quite suitable for what he wants to do. He wanted something slightly different. The board we did is, well, I don't know. It's packaged better. Supposing you want to put one of these launchpad boards in a box. You can see that this particular one that I've been using has lots of pins. And I put this sort of in a box, but this isn't a really nice looking box for something that you want to use in applications. You might not need all this stuff. You don't want to see it. You might just like to have a little push button or a power button or something, or maybe nothing at all. Well, you can do that with the boards that we made. All the parts will be on the bottom like they are on this breadboard. And on the top, it's not on this one, but it is on our board, there'll be a reset switch and a couple of other switches and a connector where you can plug in this 8 characters by 2-line display, LCD dot matrix display. And you put this in the board like this with that little bit of stuff on top that I mentioned. It's not on this one. Oh, there's a little LED there you can use to blink and show this thing's working. And that's really a nicer way to do it. If you have some, you're going to deploy a dozen of these for some particular applications or someplace, it really does work more nicely if you have a nice little board like this. I hope that answers your question. Why would anybody want to use this board? And the answer about the availability is there aren't any available now because we've only got 2, the beta version, but pretty soon we're going to have 50. I'm certainly not going to use more than about 12. And I don't know about my partner, but I doubt he's going to use very many more than that. So we might be able to sneak a couple of those. I might even give them away so I can avoid any legal issues.
How are you going to put the CAD drawing or the Gerbers, the files out as open source or open hardware?
Okay, the question was, is our little board going to be open hardware? I'm glad you asked that question. The short answer is yes. There'll be schematics, Gerber files. I have all that stuff already. It's not on the current CD, but it will be on the next one. And so the hardware is as open source as I can think of to make it. But what about the software? Well, that's a good question. I only use open source software. So microsp itself, all the source, everything you need. Like an ASM is like that too. The C version that I talked about is also, all this stuff is all open source. You can get source, you can modify it, you can do whatever you want. And by the way, a slight comment about microsp is if you want to look at the source and modify it for your own purposes, then you can do that because all the source is there. And it's all written in assembly language. For the ARM processors, you Google on something called ARM embedded. Anyway, ARM supports, sort of, an assembler and a C compiler and all that stuff for all the ARM processors, or at least all these Cortex M0, M3, M4 parts. You can download that, run it. I've done it. It all works just fine. It's easy to use, especially the assembler. So that's it. For the TI MSP 430 parts, that's also true, but it's slightly more complicated. In the assembler that he uses, he meaning Mikris, author Matthias, he uses an assembler called AS, which is freely downloadable, but installing that is quite a pain. It's not documented well anywhere. I have not been successful in installing that, but you can.
You mentioned that, I think it was 1 or 2 slides back about Micris. There's an assembler you can download and GCC.
I'm saying that the question was about the assembler or GCC for the parts that we're supporting, these FI parts, MSP 430 FRAM parts. What I was trying to make clear is if you want to program these things, there's a zillion ways of doing it. If you want to do assembler, you can download this thing called Make an ASM and read the docs, and you can have at it with assembly language. If you want to use C, you download this TI GCC thing and read the docs and get that installed. And so I'm not sure I understood the question.
The question I have is, my experience with GCC is it has assembler in it.
Oh, yes.
Which means I can do not only C, but I can also do assembly if I want to.
Okay, so the comment was that if you download the C compiler, you can embed assembly language in that directly, and that's absolutely true. And so that's another way of doing assembly language, that if you had some C code, but you wanted to do something that C doesn't support very well, you can put embedded assembler right in there, right directly in your source code. So that was a good comment, is another way of doing assembly, kind of embedded in C, if you will. Okay, one last comment is about FRAM, which maybe you weren't totally familiar with. FRAM is a relatively new technology. It stands for ferroelectric RAM. It isn't having anything to do with iron, but that's what it's called. There's lots of documentation on the TI sites. As far as I know, TI is the only microcomputer vendor that has parts with FRAM in them. Why do I like FRAM? Well, it's a non-volatile RAM. So most of us here are familiar with what's called core memory, of which there isn't any anymore except in museums. But the thing about core is you can write to it, and when the power goes off, it doesn't erase anything. When the power goes back on again, it's still there. You can read it or write it to core memory, a byte or a word at a time. And like I say, it's non-volatile, which is very different from flash. Flash is, of course, non-volatile also, meaning when the power goes off and then on again, it's still there, still programmed, but you can't write to it a word or a byte at a time. You have to write to it in whole sectors that vary anywhere from 64K bytes to 512K bytes or whatever, you know, depending on the part. And you have to program the whole thing all at once. So if there's something in the middle that, let's take the fourth word, forget, for instance, that gets rid of everything, all the fourth words that you've programmed, gets rid of all of the particular word that you're forgetting and everything after that was been programmed. Well, what if you have FRAM? If words in the middle of a sector of your FRAM, you have to erase the entire sector and then reprogram the first half of it that has this stuff in there up to that word you're forgetting. Or the other way to do it is erase or in some way forget everything past the word that you're programming, and then that flash memory is unusable, so you have a hole in your flash, and then you start new words on the next start or the next sector. That's the way Mikris does it. Now, I wrote some code to show Matthias how to do it the other way. Oh, he probably already knew. Anyway, he's a really bright guy. But he chose not to do it, and he didn't tell me why, but I think the reason may have to do with the support for the very small parts. In particular, there's a part called the MSP 430G 2553, which is in a dual inline 20-pin package, which is really nice for hobby stuff, you know. And there's a launch pad that supports that. But that has only 512 bytes of RAM. And so to save the memory that's in a sector, in the flash, to RAM, and then erase the whole sector, and then put back into that flash the part that you still need after the forget, is pretty tough to do when you only have 512 bytes of RAM and the sector is 512 bytes. You can do it, but it's a pain in the ass, and I think that's probably the reason that Matthias chose not to do that. But with FRAM, it's just like RAM, except it's non-volatile. You can read and write it a word at a time. You don't have to erase anything, just write over it, just like RAM, except it's non-volatile. So when you do a forget with FRAM, it in effect erases everything from the word you're forgetting and everything past that. And that's really nice and straightforward. There are other reasons why I like FRAM, but I don't necessarily recommend that you do it that way using one of the FRAM launchpads. You could, they're perfectly fine, but you don't really have to. For many of the applications that you might be running, or for trying the thing out, it really doesn't make much difference. My only advice is to get a part with lots of flash or FRAM. Lots meaning at least 32 gigabytes. Other than that, I don't have any particular recommendations. They're all good, really. They all have their particular advantages and disadvantages. Any questions about FRAM?
Oh, FRAM is ferroelectric RAM?
That's what it stands for. The question was, does that stand for ferroelectric RAM? The answer is yes, that's what it stands for. But again, it doesn't have anything to do with iron or ferrite. So how it got that name, I'm not sure.
Oh, it's the concept of ferroelectricity. Doesn't mean iron.
Yeah, right. The answer was it's the concept of ferroelectricity that doesn't mean iron. I'm not an expert on this, so I'll take your word for it. Good comment. Oh, one last thing about FRAM is, well, I said that TI is the only microcomputer vendor. There are various vendors who support, for instance, FRAM in parts that you can program and read from using I2C, or what's the other common one called? There's another 2 or 3 wire protocol. I2C. SPI. That's the one I was talking about, the 3-wire SPI. There are various of these parts you can buy for not very much money that support those kind of things. And heck, if you wanted to, you could buy one of these flash-based parts and add to it one of these FRAM parts, and then you could do various things like put your dictionary in FRAM or whatever. So you could get a lot of the benefits of just using an FRAM part, but you'd also have the benefits of, for instance, 512K of flash available. Which does remind me of one more thing. I have -1 minute here to go, so I'll use that, and we'll make it -2 by saying that right there it says I'm working on a resonant fourth. It is my opinion that a resonant fourth, which is what's sold by the commercial vendors, by the way, like a Fourth Inc. or what's the other big one called? MPE fourth. Those are resonant fourths. The people who are making money doing this, and in the case of Fourth Inc., have been making money doing it in that they've been in business for 20 or more years, so they're successful. They use resonant force. Advantages include it'll run on very small parts because the dictionary is not in the part, and the fourth compiler is not in the part either. It's on your PC.
So you mean a target compiler?
Yeah, target compiler, meaning that what's in the target is just the code that has to be in there for something to run. But to program it or debug it, much of the code is running on your PC instead of on the part. And not to get carried away here, but there is one implementation of Forth that is a hosted Forth called Pygmy Forth. So you can look that up. It's not, in my opinion, a particularly good implementation, but it's good enough, you know, and it runs on ARM. So you can try that out if you want to see what a hosted Forth is like. And with that, if there are no more questions, I think I'm finished.
If, as you say, you're not going to be available on the fourth day, you might want to consider finding some proxy that can make it. Just do a 5 or 10 minute overview on your behalf. John Baumgartner comes to mind. You mentioned his name. And, if he knows enough to give a quick overview, that would move the ball down the field.
Okay. Are we still online?
Yes.
Okay, so the question was about fourth day next month.
I don't have to worry about that.
Well, I want to because it relates to your question or your comment. I am unable to attend fourth day. Kevin suggested it'd be really nice if we could have some little bit of a demo or presentation or something, 10 minutes or something about Micro's fourth. And I think that's a very good idea, but I can't be there. His comment was maybe somebody else could do it. And in particular, John Baumgartner came to mind. John is unfortunately very sick. He's got cancer. Who knows how long he's going to live? I'm sorry to say, maybe not too long. I don't believe that he's capable of doing that because of his illness. But the reason I wanted this to still go on live is, yes, I think that's a great idea. So I'm looking for a volunteer, somebody who will work with me to prepare a short presentation for fourth day next month, who could do it since I can't. So send me an email if you want to do it.
Yeah, bring your boards along. Be sure.
I'm sorry, what?
Bring your boards along.
One of our boards would be, yes, would be presented. And perhaps some of these boards would be shown too. Yeah, we'll have, just like the demo today, we'll have some boards.
Consider contacting Bob Nash. And the reason I say that is he has a little enterprise with some, one or two other guys. He might be able to get out of it and sell it for you. So that
A good
you don't
idea.
have to deal with the hassle.
Quick comment. Let me see if I can find a pin here somewhere.
I can email you later.
Okay, please do that. The comment was that a guy named Bob Nash is somebody I should talk to you about, in particular about our little boards.
It doesn't sound like you're really interested in doing the commerce and enterprise part of this
Not
so
very.
much as making it available to the world. Speaking of making it available to the world, you talked about your CD. Is there some reason why you don't want to put the same material from the CD up on SourceForge, for example?
Actually, we're planning on doing that.
Okay.
The question was about putting all that stuff on SourceForge so people can get it. In the meantime, if you want one of these CDs, which I hope you don't, but if you want one, I made them, they're here. And I'll probably write on them, ignore the benchmarks, because I made a big boo-boo there. If you want a better CD mailed to you for free, no obligation, no advertising, no giving your website to any of the spammers, or your email rather. Oh, does anybody think they might want that? Because if so, I'll pass this around for you to sign up. Since you don't really need it because you can download everything. Yes.
The other thing is that you want to send your slides to Dave or just to me and I'll forward them.
Okay.
So that
I think I already
on our
did.
website going forward as part of the meeting notes.
I think I already did.
Oh, you're awesome. Thank you.
However, before you publish it, let me send you the new version. With
Make the corrections.
it's a minor correction, but it's important.
Make the corrections. Let's send them to Dave.
I already made the corrections.
Okay.
Well, but I want to add the actual benchmark results. So let me do that first, and then I'll send it.
Great.
Because it's relevant. The bottom line is, MICREST is going to be 4 or 5 times slower than assembly language, and C maybe a couple of times slower, somewhere in that ballpark. The C compiler is not a particularly optimizing one. Okay.
You know, if there's some organization or structure about the CD, you can always put an ISO of the CD up on SourceForge.
Yes,
Okay.
yes.
I'll do that, and I'll let you know when it's done.
If, you know, most folks, you know, if it's just some collection of source files and executables and you can put the bits and pieces up. But if you want to maintain some structure or overview or some guide or something, you can just put the whole ISO up and
Yeah.
propagate it that way.
CD, but I can make the USB.
Okay, and if you want to do that, you can do it with the cavat. Is that how you pronounce it? That the benchmarks are bogus.
ISO. Make sure you have SHA-256 checksums for
What kind of checksum?
SHA. It's three
Okay.
guys that came up with this way. It's,
I'll try to remember that.
the reason being is because I've had this happen. I've downloaded ISOs and I run the program checksum and it goes, oh, it didn't add.
Yeah, right. That good idea.
And it saved me from burning
Yeah. The comment was there needs to be a checksum on the ISO that I'll put on SourceForge.
The advantage,
SHA-256.
the advantage in having the ISO is you can just put the ISO on your hard drive and play it as if it were a real CD, but it's not really
Right.
wasting a CD, even the time to make it rewritable.
Yeah.
But we really want to thank
Good
you
comment.
for coming and for presenting today. And
Oh, it was
let's
fun.
go for lunch.
Great. All right. Dennis or somebody, is it safe to leave all this here? Is the room going to be locked? Great.
Let me take the microphone here from you.
Turn it off, maybe. You know how to do that.
And we are going to lunch. We'll see you this afternoon.